This video marks the beginning of our discussion of chemical quantities and specifically the mole. You may or may not remember that the mole is the SI unit of quantity. It is how we group items together and talk about how much stuff we have. Before we dive into that, one of the things that's really difficult in learning the mole is coming to grips with just how large a number a mole is and just how small are the things that you're using moles to count. And so I want to take a brief moment to talk about what I like to call the range of human intuition. How do we think about size? And there's a couple of ways to come at this. We can think about distance. For most people, when you think in terms of distance, there is this kind of range of what's the smallest thing that you can mentally picture, what's the largest thing. So the smallest thing is about 0.1 millimeters, it's about the thickness of a hair. When you get much smaller than that, you start to abstract rather than build mental images of things that are that size. And so, is it bigger than a bread box? Is it bigger than a car? Is it as big as a house? You think about objects that you call into your brain when you are given certain sizes. About the longest distance that most people will be able to conceptualize as distance is about 100 kilometers. And so there are people who, for whatever kind of a reason, decide that they want to run 100-kilometer races, and those do exist. So a single person over the course of a day could run a 100-kilometer race. And the smallest thing that we can conceptualize with distance to the largest thing that we typically conceptualize is about a factor of 1 billion. So that's 10 to the 6th. And, to kind of illustrate this point, when you think about distances over 100 kilometers, or much more than 100 kilometers, and people ask you how far away those things are, you're going to go on, say, a long road trip to grandma's house, people rarely ask you for the distance, right? At that point, we mentally convert our conception of distance to time. It's a 4-hour drive. It's a 6-hour drive. It's a 2-day drive, right? We stop thinking about it in terms of distance. We start thinking about it in terms of time because it's easier to conceptualize. We can also talk with respect to the range of human intuition about the body's ability in the sense of touch to discriminate small distances. So there is a standard kind of neurologic test called the 2-point touch test, where you take two fairly sharp needle points and you put them fairly close together on someone's skin while they're not looking, and you ask them whether or not they feel a single point of pressure or 2 points of pressure. And depending on the sensitivity of that part of their body, you're going to get slightly different results. So averages for populations, the most sensitive parts of our body are the lips and finger pads. And this would make sense. You do most of your touching with your hands, and so you would evolve to have more nerve endings there. Most people can differentiate the 2 points of pressure around 2 to 4 millimeters apart, which is that's pretty darn close. You get any closer than that, it just feels like one needle point is touching you and not two. Move from your finger pads to the palms of your hands and you lose a fair bit of sensitivity. Those needle points can be, around 9 millimeters, and you're still going to feel 1 point of pressure. Apparently, the least sensitive parts on average on the human body are your back and your shins, which is probably good. The shins are not more sensitive than they are, because if you've ever walked into a table trying to navigate a dark room at night, you know that it doesn't feel very good. So knowing that they're not super sensitive is probably a good thing. But look at how much greater that distinction is than if you've got somebody putting two needle points on your back. They can be 3 centimeters apart, and you don't notice them as 2 points. You feel them as 1 point. There's another touch test they do where they put small, sometimes they just use like little glue drops. There's like micro dots of relief on a flat sheet of paper. And so they put these little dots that are only 75 nanometers in diameter and only 1 to 2 millimeters raised off the page. Sorry, I got that flipped. They're 75 nanometers raised off the page. They're 1 to 2 millimeters in size, so it's like about the size of a print of a period on a 12-point font. and they're only raised off the paper 75 nanometers. And someone can run their fingers over the surface of that paper and feel the bump with something that small. A smallest size atom is in the neighborhood of about 0.1 nanometers. So you're only 100 times larger than that, and our fingertips can distinguish objects that size. So we have a very sensitive sense of touch, but nanometers are only 10 to the negative ninth. So you got a factor of 10 to the ninth there. And so we're still dealing with fairly small and mentally conceptual numbers. The next thing we'll look at is sense perception with respect to vision. And so how many colors you can see are related to the number of cone cells you have in your eyes. So there's two kinds of cells in your eyes, cone cells, rod cells. The cones help you distinguish color. The rods help you distinguish light and dark. And so animals who have what are called monochromacy can only have one type of cone cell, and they can only distinguish about 100 different colors in the world. This is about your ability to discriminate between different wavelengths and perceive them in your brain as something different. Dichromacy means you have two types of cone cells. That allows you to see about 10,000 colors. Humans are trichromacy. We have three different types of cones in your eyes, and so humans can differentiate up to 1 million colors. That's a lot, but again, that's 10 to the sixth, which is a big number. But in a second here, when we talk about the mole, you'll see how this number is so much bigger than that. Again, monochromacy and dichromacy are versions of color blindness. So people that don't have three functioning types of cone cells are going to have a reduced color discrimination because of the types of cone cells they have. There are animals that have tetrachromacy, means they have 4 different types of cone cells. They can see up to 100 million. So you're going to get certain birds, certain insects can do this. Pentachromacy has 5 cone cells, so they presumably can distinguish up to 10 billion, which is pretty big. So if you had 5 cone cells, you could make a killer wicked box of gel pens. And so all of this, again, is to get us to start thinking about big numbers or really small numbers, right? We talked about the size of the microdot being 10 to the negative ninth. We talk about our sense of distance being on a factor of 10 to the sixth. And so keep kind of these things in your brain as we move on to talk about measuring stuff. So when we talk about measuring stuff, in the chemical lab in particular, but in the world in general, there are really 3 primary ways to tell how much stuff you have. And so one of them is to count particles. How many individual units of whatever it is that you're counting do you have? And in order to do that, you have to define the unit, right? So if we look in the bottom right of this picture, we might talk about buying apples by the individual piece of fruit. But if we were to count those in terms of their potential to make apple trees, we would want to count the number of seeds inside. And so we would be counting a different kind of thing, depending on what it is you're wanting to investigate. We might then also buy those apples rather than by the each. We would buy them by the pound. And that tells you something about how much you have when you weigh something out. And then our third picture here is going to tell us something about volume. How much space does something take up? And so that is another way to tell you how much you have. A half gallon of milk is not as much milk as a full gallon of milk, right? So that's one way to tell us how much stuff we have. When we're talking about atoms and how much stuff we have, we're going to talk about relative atomic mass. Relative atomic mass is the number you see on the periodic table, the little decimal that's usually under the element symbol, and that is considered that element's weight or mass. So there are 2 ways to interpret this relative atomic mass. You can interpret it as what is referred to as the atomic mass, and that's the average mass of a single element of that substance in AMUs, or what are referred to as atomic mass units. An atomic mass unit is set so that roughly a proton weighs 1 AMU. So when we look at this vanadium square of the periodic table up here on this slide, and it has a mass of 50.9415, that means the average vanadium atom is around 51 times bigger than a proton. The second interpretation of this is called the molar mass. The molar mass is the mass of 1 mole of that element in grams. So we would count out a mole, which is a specific quantity. Think a mole works a lot like a dozen. When we say we have a dozen of something, it means 12. And it doesn't matter if it's a dozen donuts or a dozen apples. It's 12 of whatever the thing you're counting. So in this case, if we had a dozen atoms, it would be 12 atoms. But a dozen atoms would not be measurable under really under any circumstances. And so we scale that up significantly with the mole. And so a mole of atoms is a certain number of atoms, and it's the same no matter what the type of element is. So a molar mass is how much a mole of those atoms would weigh in grams. So the units there are going to be grams, or they're going to be grams per mole. And so when you look at the number on the periodic table, if you pull that number off with no units, it's considered the relative atomic mass. It's how many times bigger that thing is than a proton. If we want to actually give it a mass with a unit, we call that thing an atomic mass, and so that's measured in AMUs. Those AMUs could be converted to grams if you had a conversion factor between them, but 50.94 AMUs is the mass of 1 vanadium atom. If you put units of grams on that number, then we have what's called the molar mass. I want you to notice that the square says 50.9415, but my slide here says 50.94. What we are going to do in this class for the sake of consistency is always round masses on the periodic table to 2 decimal places. That's not a rule of chemistry, that's just a rule for our class, so that every time we do the calculations, we all get the same answers. So relative atomic mass is always rounded to 2 decimal places. Real quick, just for a definition for you there, how do you get an AMU? An AMU, by definition, is 1/12 the mass of a carbon-12 atom. And so if you think about this, a carbon-12 atom is 6 protons and 6 neutrons, which don't exactly weigh the same, although they're close. And so an AMU is essentially the average mass between the mass of your average proton and average neutron. And so we talked about the conversion there. Then if you needed to convert that to grams, then 1 AMU is 10 to the negative 24th grams, which is pretty tiny. Again, think about how much smaller that number is than the numbers we were talking about at the beginning of this lab. And that gets you to what is a mole. And this, again, is one of the hardest things to conceptualize for people who are learning chemistry. Really, people, it's hard to conceptualize. Because when we talk about a mole, we're talking about a quantity that equals 6.02 times 10 to the 23rd. That RP stands for representative particles. So it could be apples. 6.02 times 10 to the 23rd apples. Just like a dozen is 12 apples. It could be pickup trucks. A mole of pickup trucks is 6.02 times 10 to the 23rd. But we're usually talking about atoms, molecules, and whatnot. So when we say representative particles, we mean our list of particles that we have already learned. Either atoms or ions or molecules or formula units. And these things are really, 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 really small. And so, again, the conceptualization here is that we're talking about absurdly large numbers, 10 to the 23rd, of really, really small things that are submicroscopic. And so we're working way past both ends of our range of human intuition. This number of particles, 6.02 times 10 to the 23rd, is also sometimes referred to as Avogadro's number, in honor of Amedeo Avogadro, who wrote a paper that really kind of introduced and situated this idea of how to go about counting particles that are below the ability of humans to measure ever. It isn't a lack of technology. It's that they're below the smallest wavelength of visible light, so they're unmeasurable. And he sorted out kind of a conceptual approach to how we would go about doing that. And if you look at the dates that we're talking about here, this is the late 18th into the mid 19th century. So this is well before microscope technology was super advanced. So it was a pretty clever approach. And that's what we'll talk about a little bit in our next video.